Narrator voiceover. Imagine a world where artificial intelligence doesn't just mimic human thought, but fundamentally transforms how we solve problems. From decoding the human genome to predicting climate shifts, the latest breakthroughs in AI are rewriting the boundaries of what's possible. But how do these systems actually work? What's driving the next wave of innovation? Let's dive deep into the cutting-edge research shaping the future of AI. No fluff, just the technical guts. Segment 1, the rise of transformer architectures. Let's start with the backbone of modern AI, the transformer. You've heard the term, but here's the technical heartbeat. Unlike traditional neural networks that process data sequentially, transformers use self-attention mechanisms to weigh the significance of every input element simultaneously. Think of it as a team of specialists, each focusing on different parts of a problem while sharing insights in real time. The key innovation: the attention matrix. For a sequence of tokens, like words in a sentence, each token's representation is dynamically adjusted based on its relationship with every other token. This allows models to capture long-range dependencies, a game-changer for tasks like machine translation or code generation. And with techniques like sparse attention or axial attention, researchers are now scaling these models to trillions of parameters without sacrificing efficiency. Transition. But transformers aren't just about scale. They're evolving in ways that blur the line between computation and cognition. Segment 2, Neural Architecture Search NAS and AutoML. Here's where AI starts to design AI. Neural Architecture Search automates the creation of neural network structures using reinforcement learning or differentiable methods. Instead of humans handcrafting layers, NAS algorithms evaluate thousands of architectures, optimizing for metrics like accuracy, latency, or energy consumption. Take one recent breakthrough, differentiable NAS. By approximating discrete network choices with continuous gradients, researchers can train architectures using standard backpropagation. This isn't just faster, it's unlocking designs that defy human intuition. For example, a 2023 paper demonstrated a CNN architecture for medical imaging that outperformed human-designed models by 12% while using 30% fewer parameters. Transition. Now let's talk about a frontier where AI meets physics, differentiable simulators. Segment 3, Differentiable Physics and Embodied AI. Traditional AI struggles with real-world dynamics. But differentiable simulators are changing that. These systems integrate physical laws, like Newtonian mechanics or fluid dynamics, directly into the training process. By making simulations differentiable, models can learn from raw sensory data while respecting physical constraints. Imagine a robot learning to grasp objects. Instead of simulating millions of trials in a virtual environment, a differentiable simulator allows the robot to adjust its actions based on real-time feedback from a physics engine. This isn't just theoretical. A 2024 study showed a robotic arm using this approach could adapt to novel objects in under a second, a leap forward for embodied AI. Transition. But what if the data itself is the key? Let's explore the rise of self-supervised learning. Segment 4, Self-Supervised Learning and Contrastive Pretraining. Labels are expensive. Self-supervised learning solves that by using the data itself as a teacher. Take contrastive pretraining. Models learn to distinguish between similar data points by maximizing the similarity of augmented views of the same input, while minimizing similarity with unrelated examples. This is where techniques like MoCo, momentum contrast, shine. By maintaining a dynamic dictionary of negative samples and using a momentum encoder to stabilize training, MoCo achieves state-of-the-art results on tasks like image classification with no labeled data. And it's not just images. Self-supervised methods are now outperforming supervised models in speech recognition, NLP, and even scientific discovery, like identifying protein structures from raw sequences. Transition. Yet as these systems grow more powerful, a critical question emerges. How do we ensure they're reliable? Segment 5, Robustness, Safety, and Alignment. AI isn't just about capability, it's about control. Researchers are tackling robustness through adversarial training, where models are exposed to perturbed data to improve resilience. For example, a 2023 paper demonstrated a vision model trained on adversarial examples that achieved 99.8% accuracy on standard benchmarks while resisting evasion attacks. But safety goes deeper. Techniques like reinforcement learning with human feedback, RLHF, and value alignment frameworks are aligning AI behavior with human values. One promising approach: inverse reinforcement learning, where models infer reward functions from human demonstrations. It's not perfect, but it's a step towards systems that don't just optimize for metrics but understand the why behind them. Closing. The future of AI isn't just smarter, it's more adaptive, more efficient, and more intertwined with the physical world. From transformers that think in parallel to self-supervised models that learn from the noise of existence, the field is evolving faster than ever. But with great power comes great responsibility. As researchers push boundaries, the challenge remains. How do we build systems that are not only powerful but also trustworthy? The answer lies in the details and the next generation of innovators. What will you build? Text on screen voiceover. Thanks for watching. Hit subscribe for more deep dives into AI's toughest challenges and breakthroughs. The next revolution is coming, and it's powered by curiosity.